In this video I'm using a light bulb device and it has a plug. But when you plug this light bulb in, it doesn't turn on. When we look inside, you might understand why. There are a couple wires here that are not connected, so there is no electrical circuit, and therefore the light bulb doesn't go on. If we connect these wires with something conductive like these tongs, the light may go on. There it is, the light is on. So once a connection is made, we have an electrical circuit and electricity flows. This device is meant to test solutions that can go in a beaker. Imagine we have some liquid, we dunk the light bulb device in, and determine whether the solution is conductive. The first solution we'll test is tap water. So here's water from the faucet, put it in the beaker, and this is ready to dunk the light bulb device in. Here we go, and there's a light. It's not a very bright light, but there's definitely a glow. Here I'll zoom in, and you can see the filament is glowing. This level of conductivity is small, it's low. We call this slightly conductive. So tap water is slightly conductive. The next test we'll use distilled water instead of tap water. And on this one, I want you to make a prediction. How do you think the conductivity of distilled water will compare to that of tap water? Pause the tape, make a prediction. Here are the results with the distilled water, and there is no light at all. So distilled water is not conductive. So either distilled water is lacking something needed to make conductivity, or distilled water has something special in it that prevents conductivity. For the next test, we'll add some salt to the distilled water. Here's some table salt from Albertsons. Table salt is chemically sodium chloride. And we can add a scoop to the water. 1 scoop, 2 scoops. How about a third just for good luck? And this is a soluble salt, so we'll stir it up and the solid will all dissolve. Now it's all dissolved. Retrieve the bean and we're ready to test. Here's the light bulb device, and you can see, and now it's really bright, much brighter than tap water. So dissolving salt in the distilled water has vastly increased its conductivity. So now we can make some conclusions. We saw that distilled water, pure H2O, was not conductive. And we saw that dissolving salt in the water made it very conductive. So this can lead to the hypothesis that ions dissolved into the solution make it conductive. Specifically, it's ions that can move. Ions that move can carry charge through the water, and this is a form of an electrical current. So originally there were 2 wires that were not connected. When there are ions in solution, the ions can flow, completing the circuit, and allow the light bulb to light up. We can now explain the small glow seen with tap water. Tap water has some ions in it, not nearly as many as salt water, but enough to provide a small level of conductivity and therefore a dim glow. To explain conductivity, we can look at a model. So here is a lattice of sodium chloride solid, and I'm hoping you remember the motto, when the salt is dissolved, the bond is dissolved. So in aqueous, these ions are no longer bound to each other. They are free to move. And that's what makes the conductivity in a solution of sodium chloride. These ions can move any which way they want. A simple way to express this without all the symbols would be NaCl, which is solid, turns into Na plus, aqueous, and Cl minus, aqueous. When the salt is dissolved, the bond is dissolved. For the fourth test, we'll use some dilute hydrochloric acid, HCl. Here I'm taking a bottle of 1 molar HCl and adding a little bit to a beaker of distilled water. So it's now maybe about 0.1 molar HCl. You'll recall that HCl is a strong acid. Based on this, make a prediction of the conductivity of this solution. Pause the tape, make your prediction. Here now are the results. It's bright, very bright. This means there must be many ions in this solution. Here we have HCl, one of the strong acids, and water. You should remember that water is an amphoteric substance. It can act as an acid, it can act as a base. In this case, it must act as a base, because HCl can only act as an acid. So here, one of the products will be the hydronium ion, H3O+. It's an ion. That's what's important here for conductivity. And there will also be the chloride ion all by itself. And this reaction goes one way, 100% dissociation of the HCl. So therefore, everything will be here, all ionized. Exclamation point. And these are the ions that conduct electricity, make the light go on. Test number 5 is dilute acetic acid. This is a weak acid. What I have here is some 1 molar acetic acid. This is about the same concentration you would get in vinegar. I'm now diluting the acetic acid into distilled water. Acetic acid is a weak acid, not a strong acid. So a weak acid will not force its hydrogen ion onto a water molecule. With that in mind, make a prediction for the conductivity of this solution. Here now are the results of the dilute acetic acid. You should see a very dim glow there. So this dim glow shows that the acetic acid solution is slightly conductive. There must be a few ions in this solution. This is now acetic acid. The COOH part you should be able to draw well. COOH, carboxylic acid. The CH3 on the left is a tetrahedron. With water. So we just saw water acting as a base with the hydrochloric acid. And the same thing can happen here, but acetic acid's a weak acid. So let me show you what that means. There will be a few hydronium ions in the solution. By random chance, a few of these H's here will be transferred to water. That will result in hydronium and acetate. This is the acetate ion, a carboxylate ion. Those of you who understand resonance, you should see that this can resonate here. resonate. All right, so these are ions. But you should readily see the possibility of reversal. So there's going to be a big arrow coming back to the left, meaning hydronium ion will readily donate its proton back to acetate, and you'll go back to the left side. So with this, we get an equilibrium. Equilibrium does not mean 50-50. In this case, with the weak acid, about 1% of the molecules will be in the ionized state, 1%. And 99% will be in the unionized state. But these few ions made the dim glow. Exclamation, exclamation, exclamation. That's what you saw in the demonstration. For test number 6, we'll use some ammonia. You should recall that ammonia, NH3, is a weak base. So now you need to predict, will there be any ions in this solution? Ammonia itself is uncharged. It is not an ion. It's not a salt. It's not an acid. Is there any way it could produce ions in this solution? Make a prediction, make an argument. Will there be ions in this solution or not? Here are the results. There it is, a dim glow, slightly conductive. There must be ions in this solution. Where did they come from? Here is ammonia, NH3, in water. So here I will represent ammonia as a pyramid shape. It has these 2 electrons on top. There's ammonia, and it is a base. A weak base, a weak base. So let's represent the water molecule. In this instance, water will act as an acid, not as a base, but as an acid. So this H here has the possibility of being transferred to the base. If we do that, you should see that the water will be left as just OH with a minus. The ammonia will become NH4 with a plus. These are ions. These products can conduct electricity. But once again, you should see that this is reversible. Hydroxide will readily steal the proton back from the ammonium ion. So this is actually a very large arrow here, going back to the left. And therefore, once again, we'll have a situation where 99% are in the unionized state. And only 1% or so will be in the ionized state. And that means, again, few ions. Dim light. This last test is counterintuitive. I'm going to mix the weak base, NH3, and the weak acid, CH3COOH. Here I'm testing the weak acid, show you it's slightly conductive. Here's the ammonia solution, slightly conductive. Now I'm putting the conductivity device in an empty beaker in the middle, and I'll pour the two solutions in. Dim plus dim. Wait for it. It's bright. So this is a very interesting puzzle for you to figure out how can dim plus dim equal bright.